At this very moment, a colossal storm, Super Typhoon Sinlaku, is making landfall on American islands that have yet to fully heal from their last major catastrophe. As a Category 5 cyclone with winds reaching 173 miles per hour, it stands as the most powerful storm currently spinning anywhere on Earth. For more than 9 consecutive hours, the international airport on Saipan has been recording winds consistently above 120 miles per hour. And yet, what is truly unsettling is that this sustained, destructive force was merely the prelude. The eye wall, the storm's most ferocious component, had not yet even made its arrival. As if this were not enough, a magnitude 5.5 earthquake also shook the island chain just 6 hours before the typhoon's impact. While this crisis unfolds in the Pacific, other parts of the United States are simultaneously facing their own extremes. Record heat on the East Coast, tornadoes across the Midwest, and wildfires sweeping through the plains. This convergence of events on a single day raises a profound question. Is this a glimpse of a new reality, or simply the opening chapter of a more volatile era? This story is only just beginning to unfold. To follow our continued exploration of these powerful planetary events, we invite you to join us here at Calm Space. The situation raises a critical question about our climate system. If this is what can be produced in April, during a neutral year before El Niño has even entered the picture, what might the peak of the season now look like? Right now, as we consider these events, the planet's strongest storm is tearing across United States territory, a crisis unfolding largely unnoticed by the mainland. The measurements from Saipan International Airport tell a story of relentless force, sustained winds exceeding 120 miles per hour for 9 straight hours. This is not a momentary gust or a peak reading that quickly subsides. It is a 9-hour siege, powerful enough to shred commercial roofing, snap utility poles like kindling, and transform everyday objects into projectiles, moving with incredible speed. But the most sobering part of this reality is that these 9 hours of destruction occurred before the eyewall even arrived. It is a scenario akin to enduring a prolonged, punishing assault, only to learn that the main confrontation has yet to begin. In response, the National Weather Service has issued an extreme wind warning for the islands. If you are unfamiliar with this alert, there is a good reason. It is almost never used. This is the rarest and most severe wind warning in the entire American forecasting system, reserved exclusively for the inner core of the most violent cyclones, where sustained winds are expected to meet or exceed 150 miles per hour. It is a declaration that carries immense weight, signifying a moment when the atmosphere outside is no longer survivable by any conventional measure, and the only remaining action is to seek shelter within a reinforced concrete structure. That warning is currently active over American soil. Radar imagery from Anderson Air Force Base on Guam is now confirming what forecasters had feared. The eye wall is not delivering a glancing blow or passing to one side. Instead, it is making a direct passage over the island of Tinian, while the outer edge of that same violent core rakes across Saipan. This means 2 populated islands are simultaneously caught within the most destructive part of the storm, a truly devastating trajectory. To understand the true nature of the damage, we must consider a principle from structural engineering known as fatigue loading. This concept explains that buildings and infrastructure do not always fail from a single overwhelming force. More often, they fail because of repeated cycles of stress. A beam pushed one way, then the other, and back again thousands of times will eventually give out, not because any single push exceeded its design limit, but because the cumulative load wore through its resistance. This is precisely what more than 9 hours of hurricane-force winds inflict upon a building. With every gust, the roof flexes and the walls are pushed. Fasteners loosen, joints separate, and microfractures spread through concrete. By the time the eye wall arrives, with winds 50% stronger, the structures are no longer at their full design strength. They have been systematically weakened. Just as the true force of the storm makes its appearance. The wind is not the only weapon in this storm's arsenal. Rain has been falling at rates between 1 and 2 inches per hour across the island chain. On a flat continental plain, this might be manageable, as storm drains and rivers can handle the volume. But Tinian and Saipan are small volcanic islands with steep interior terrain and thin layers of soil over rock. Water has little place to soak in. It runs off with incredible speed down slopes, across roads and through structures, carrying mud and debris with it. Flash flooding was already underway long before the most intense bands of rain arrived, a problem compounded by drainage systems that were already compromised by previous typhoons. And then there is the ocean itself, rising up to meet the land. Storm surge forecasts have called for 10 to 15 feet of water above normal tide levels, while waves offshore are running at 40 feet. The reef systems that typically act as a natural breakwater, absorbing some of that wave energy, are being completely overtopped. This allows the full, raw power of the open ocean to strike the coastline with almost nothing to slow it down. Coastal structures are taking direct wave impacts on top of the surge, which is itself on top of the torrential rain and catastrophic wind. It is a cascade of hazards, each one stacking on top of the last, with no reprieve. Perhaps the most dangerous characteristic of this event is one that separates it from many storms covered in the news. This is not a hit-and-run typhoon, racing across the islands to deliver a brutal but brief punishment. Instead, this storm is moving at a crawl, sitting atop these islands like an immense weight pressing down. Every hour it lingers, the damage compounds in ways that are not linear. We are not just witnessing a powerful typhoon that chanced upon some islands. We are seeing the most potent cyclone currently active on the planet. Its existence in April, well outside the typical peak of the season, challenges our understanding of what the climate system is now capable of producing. The most powerful storm currently on our planet has a name: Super Typhoon Sinlaku. At its peak, the storm achieved sustained winds of 173 miles per hour. It is a figure that demands a moment of quiet contemplation. For those outside the United States, that translates to 278 kilometers per hour, a velocity that surpasses the cruising speed of some propeller-driven aircraft. These are winds capable of generating forces that exceed the design limits of most homes and commercial buildings ever constructed on these islands. In the moment of its peak intensity, Sinlaku stood alone. No other tropical cyclone anywhere on Earth, whether in the Atlantic, the Indian Ocean, or the Southern Hemisphere, came anywhere near its power. It was, quite simply, the strongest storm on the planet. Here on Calm Space, we avoid using superlatives for dramatic effect. So it's important to place this storm's power into a meaningful framework. The Joint Typhoon Warning Center in the Western Pacific designates any typhoon with sustained winds of 150 miles per hour or more as a super typhoon, an equivalent to a high-end Category 4 or a Category 5 hurricane. Sinlaku did not merely cross this threshold, it soared far beyond it. With winds of 173 miles per hour, it sits comfortably in the upper echelon of super typhoons, a level of intensity that historically appears only a few times in a decade. And yet, all of this strength appeared in April. This single detail reframes the entire narrative of the storm. April is not supposed to be typhoon season. The primary season for cyclones in the Western Pacific typically runs from July through November, with activity peaking in August, September, and October. That is the period when the ocean has had an entire summer to accumulate thermal energy, when atmospheric moisture is at its highest, and when the monsoon trough creates favorable conditions for rotation. By contrast, April marks the end of the dry season in the Marianas. It's a month where one might observe a weak tropical depression faltering as it crosses the basin. What one does not expect to see is a super typhoon with winds of 173 miles per hour. The reason this timing is so critical is because the timing times the story. A Category 5 storm in September is a terrifying but known phenomenon. A Category 5 inches April, however, serves as a signal. It suggests that the climate system is changing and that the old, predictable calendar, with its clear start and end dates for hurricane season, is becoming increasingly unreliable. To find any parallel in the historical record, one must look back to Typhoon Hester in 1966. That storm formed in late March and intensified into a super typhoon in early April, making it one of the only other documented instances of such early season intensity. But that was nearly 60 years ago. And it was widely considered a statistical anomaly, a freak event in a dataset too limited to draw firm conclusions from. The arrival of Sinlaku in 2026 makes that pattern much harder to ignore. When such outliers begin to repeat, they cease to be outliers at all. The sheer energy contained within a storm of this magnitude is almost beyond comprehension. A mature super typhoon releases thermal energy at a rate that dwarfs anything humanity has ever engineered, equivalent to several times the total electrical consumption of a major industrial nation, sustained for days on end. The storm operates as a colossal heat engine, drawing thermal energy from the ocean's surface and converting it into kinetic energy in the form of wind, while radiating waste heat from its top into the upper atmosphere. The efficiency of this engine is dictated by its fuel source, and that fuel is the heat stored in the ocean. Under normal conditions in April, the waters of the Western Pacific have not yet stored enough heat to power such an engine at its maximum output. While the surface layers may be warm, this warmth does not extend deep enough. As a storm intensifies, it churns the ocean, bringing cooler water up from below and effectively cutting off its own fuel. This process acts as a natural braking mechanism, but in this case, that mechanism has failed. The reason for its failure is a crucial part of this story, as it connects this individual storm to a much larger pattern emerging in climate data, event after event, year after year. It raises an unsettling question. If April can produce a super typhoon with 173 mile per hour winds, what might the peak of the season now look like? There is a number buried deep within the forecast data for Super Typhoon Sinlaku that is more significant than its wind speed or its central pressure. It is a variable that most people scrolling past the headlines will likely never notice, yet it is profoundly important. That number is its forward speed, 3 knots. This translates to roughly 3.5 miles per hour, or about 5.5 kilometers per hour. To put that into a tangible perspective, it is slower than a person's casual walk. You could, at this very moment, get up and easily outpace this Category 5 super typhoon on foot. It is this glacial pace that elevates the storm from a severe threat to a potential worst-case scenario. When we discuss the damage from tropical cyclones, the public conversation almost invariably centers on wind speed. The labels we use, Category 1, Category 3, Category 5, are based entirely on the maximum sustained winds. And while wind speed is undeniably critical, producing greater force on structures and more airborne debris, it represents only one half of the equation. The other half, the one that keeps emergency managers awake at night, is duration. How long must a community endure the storm's core? For how many hours will those winds batter the same buildings, the rain saturate the same watersheds, and the surge push water into the same coastal streets? A Category 5 typhoon, moving at a typical forward speed of 20 knots, might subject a given island to its peak conditions for 2 or perhaps 3 hours. While still catastrophic, the event is bounded. the storm arrives, unleashes its fury, and moves on, allowing emergency response to begin within hours of the eye wall's passage. But with Sinlaku crawling at just 3 knots, that same island could face eye wall conditions for 8 to 10 hours, or possibly even longer. The mathematics of rainfall alone illustrate the terrifying implications. At a rate of 1 to 2 inches per hour, which has already been observed, a 3-hour passage would deposit 3 to 6 inches of rain. This is manageable for some areas and dangerous for small islands, but it remains within the realm of historical precedent. A 10-hour passage at that same rate, however, delivers 10 to 20 inches of rain, and that is a conservative estimate. The official National Weather Service forecast for this event projects 15 to 25 inches of total rainfall across the Mariana Islands, with some localized areas potentially seeing even more. This is where the non-linear nature of a disaster begins to reveal itself. Doubling the amount of rainfall does not simply double the flood risk, it can multiply it exponentially. When rainfall becomes too intense for drainage systems, its destructive potential can multiply by a factor of 5 or even 10. Once the engineered channels are overwhelmed, any additional rain has no place to go but overland, surging through buildings, cascading down slopes, and inundating entire communities. This effect is dramatically amplified on volcanic islands like Tinian and Saipan, where the very terrain becomes an accomplice to the flood. Steep hillsides shed water almost instantly, and a thin layer of topsoil over volcanic rock offers virtually no absorption. Here, the water transforms into a gravity-powered weapon, gathering speed and debris as it carves new channels where roads once lay. This brings us to the central, most alarming feature of this storm. It is not just powerful, but agonizingly slow. In the context of a tropical cyclone, slowness is a multiplier, transforming every other hazard from dangerous into something potentially unsurvivable. For a mainland parallel, one might recall Hurricane Harvey in 2017. That storm stalled for days over the Houston metropolitan area, unleashing more than 60 inches of rain in some areas. It was not Harvey's wind that etched it into history as a catastrophic disaster. It was the simple fact that it stopped moving. The cyclone sat over one of America's largest cities and delivered relentless rain, producing floods unlike anything modern Texas had ever witnessed. The storm left behind over $100 billion in damage and claimed more than 100 lives, the majority lost to drowning in floodwaters, not to the wind. While the geography and population of the Mariana Islands are vastly different and the storm dynamics are not identical, the underlying principle holds true. When a tropical cyclone ceases its forward motion, duration eclipses intensity as the primary engine of destruction. This prolonged assault is compounded by the storm surge. Under normal circumstances, a storm surge is a fleeting event. The cyclone pushes a dome of water ashore as it makes landfall, and this water recedes as the storm moves past. But with a slow-moving system, the surge does not retreat. It lingers for hours on end. Water that would typically drain back to the sea remains pressed against the coastline, submerging everything near the shore for far longer than any structure or landscape is meant to withstand. A surge of 10 to 15 feet lasting for 1 hour is devastating. The same surge lasting for 8 hours is transformative, capable of permanently reshaping the coastline itself. And with every hour this storm lingers, it grinds away at the same infrastructure, the same buildings, power systems, and communication networks that were already weakened before the storm even reached its peak. It is a crucial detail that these islands endured 9 hours of hurricane-force winds before the eye wall even arrived. This means the structures now being battered by the storm's most ferocious core are not at their full design strength. They are already damaged. It raises a sobering question. How can anything withstand such a prolonged siege? They are absorbing the worst blows of the fight with their defenses already broken. This is not merely a test of strength, but a battle against time under immense pressure. And for the islands absorbing this impact, their recent history makes an already dire situation profoundly worse, because they were never fully whole to begin with. In October of 2018, Super Typhoon Yutu scored a direct hit on Tinian and Saipan, unleashing sustained winds of 180 miles per hour. It was the most powerful tropical cyclone to strike any part of the United States, since modern record-keeping began not just for that year, or in the Pacific, but the strongest ever to make landfall on American soil. Yutu effectively flattened Tinian. Surveys conducted after the storm revealed that the vast majority of structures on the island had sustained damage ranging from significant to catastrophic. Concrete buildings had their roofs torn away, while wooden homes were reduced to scattered fields of debris. The power grid did not simply fail, it was physically annihilated. Transmission poles snapped, and distribution lines were ripped from their anchors, rendering the entire electrical network useless in a matter of hours. Communications infrastructure collapsed in tandem. Cell towers were toppled or stripped of their sensitive equipment, and landline networks were completely severed. In the days following Yutu, Tinian was effectively isolated from the outside world. This was the stark reality. An American community in the 21st century had been reduced to pre-industrial means of communication. The recovery from that storm was long, costly, and ultimately incomplete. While federal disaster assistance was provided, the Commonwealth of the Northern Mariana Islands, or CNMI, is not a wealthy territory. Its local economy is small, heavily reliant on tourism and federal support, and the administrative infrastructure needed to oversee a reconstruction of that magnitude was simply not in place. Consequently, buildings were often patched up rather than rebuilt to modern, more resilient codes. Temporary fixes slowly became permanent solutions. Restoring power took months in some areas, and even after the grid was declared functional, it remained fragile and susceptible to disruption from far less severe weather. Then, in 2023, Typhoon Mawar passed near enough to Guam and the southern Marianas to inflict yet more damage on systems still recovering from Yutu. This meant another round of repairs, another drain on finite resources, and another set of buildings weakened, patched, and weakened again. This pattern of repeated damage and incomplete recovery defines the struggle for survival in the CNMI. It is this very cycle that makes Super Typhoon Sinlaku so much more dangerous than its wind speed alone might indicate. The islands absorbing this impact are not starting from a stable baseline. They are starting from a profound deficit. Every structure still standing today has a history of trauma written into its walls, patches layered over patches, repairs just good enough to pass an inspection, but never sufficient to withstand another direct hit from a Category 5 storm. The concrete that survived Yutu has since endured thousands of thermal expansion and contraction cycles, constant salt exposure, moisture infiltration, and the low-grade seismic activity of a volcanic island chain. It is simply not the same material that was poured when those buildings were first constructed. This reality is perfectly captured by a concept that disaster researchers have been discussing with growing urgency, one they call the recovery gap. This idea crystallizes the precarious situation we are witnessing. The recovery gap is the space between how long it takes for a community to rebuild and how frequently the next disaster strikes. When the recovery period is shorter than the return interval between storms, communities have a chance to fully restore their infrastructure, their economy, and their social fabric. But a terrifying dynamic emerges when storms arrive faster than communities can rebuild when the recovery gap closes, or worse, inverts. This creates what is known as a ratchet effect. Each successive disaster pushes the community's baseline resilience lower. Each recovery effort reaches a slightly lower ceiling than the one before. Over time, the community is not truly recovering at all. Instead, it becomes trapped in a downward spiral, its capacity to withstand the next inevitable blow diminishing with every storm that passes. It is a slow, grinding process of attrition. where survival itself becomes the only measure of success. The Commonwealth of the Northern Mariana Islands finds itself in a state of managed decline, weathering successive disasters with an ever-decreasing ability to withstand the next. It is a community caught in a perilous gap between destruction and recovery. Consider the timeline. Cyclone U-2 in 2018, Moya in 2023, and Sinlaku in 2026. 3 catastrophic cyclones within just 8 years. Each storm strikes infrastructure already compromised by the one before it. The arithmetic of this reality is unforgiving. It is simply not feasible to completely reconstruct a power grid, housing, water systems, and transportation on a remote Pacific island in 3 to 5 years, all on a finite budget while sustaining essential government services. Instead, what occurs is a form of triage, where only the most vital systems receive partial repairs and everything else is left to degrade. Now, a super typhoon with 173 mile per hour winds is bearing down on this fragile network, grinding away at it for 8 to 10 hours. This raises a critical question, not of whether the islands can endure, but why such storms are arriving with a ferocity and frequency that outpace any possible cycle of rebuilding. To find the answer, we must look beneath the surface of the waves. Every tropical cyclone on our planet is powered by a single fundamental fuel source: warm ocean water. If you strip away the satellite views, radar animations, and wind speed data, what remains is the elegant physics of a heat engine. The ocean supplies the thermal energy, and the atmosphere transforms that energy into motion. The storm we see is merely the visible manifestation of this immense energy conversion. It is a process that reminds us of the deep connection between the sea and the sky. However, not all fuel is of the same quality. The oceanic conditions beneath Super Typhoon Sinlaku were profoundly abnormal, which helps explain not only the storm's existence, but also its staggering intensity. In a month where it should have been impossible, the ocean heat content along its path was measured between 125 and 150 kilojoules per square centimeter. To place that figure in perspective, the widely accepted minimum for sustaining a tropical cyclone is about 50 to 60 kilojoules per square centimeter. The threshold for rapid intensification, the explosive growth that can transform a moderate storm into a Category 5 monster, seemingly overnight, is approximately 80 to 100. This means Sinlaku was traveling over an energy source that was 50 to 75% above the level needed for such explosive development. During April, the sea surface temperatures along the typhoon's trajectory hovered between 28 and 29 degrees Celsius. This is above the conventional 26 to 27 degree threshold required for a tropical cyclone to form. While warm surface waters are not entirely unusual for the Western Pacific, even in the spring, the truly decisive factor was not at the surface. The real story of this storm's power was hidden in the depths below. Under normal circumstances, a powerful typhoon often becomes its own greatest adversary. Its intense winds churn the ocean, mixing cooler water from the depths up to the surface in a process known as upwelling. This action lowers sea surface temperatures directly in the storm's path, effectively cutting off its supply of thermal energy. It is a natural negative feedback loop. The more powerful the storm becomes, the more it disrupts its own fuel source. This is the reason many typhoons reach a peak intensity and then begin to weaken, even when atmospheric conditions are still favorable. The ocean itself essentially pulls the plug. In the case of Sinlaku, the ocean never pulled that plug. The reason for this lies in the sheer depth of the warm water. Beneath the storm's track, the layer of warm water extended far deeper than is typical. Instead of a shallow, warm layer resting atop a cooler thermocline, the heat penetrated far down into the water column. So, when Sinlaku's winds churned the surface, the water that mixed upward was still warm. The negative feedback loop that should have constrained the storm's intensity never activated. The question then becomes, what happens when a natural safety mechanism is disabled? The storm just kept drawing energy, continuing to intensify and sustain winds that should have been physically impossible for this time of year. This phenomenon is what oceanographers call the warm pool expansion in the Western Pacific. That vast expanse of water exceeding 28 degrees Celsius, which is a primary driver of global weather patterns, has been expanding in both area and volume for decades. It is not merely spreading out geographically, it is also becoming deeper. This means more heat is stored deeper within the water column, remaining available for longer periods and resisting the self-limiting processes that once moderated early season storms. This trend connects directly to the central mystery of this entire event. A super typhoon in April should not have access to this quantity of energy. The seasonal accumulation of solar heating should not have driven ocean heat content to such extreme levels so early in the year. But the ocean is no longer resetting to a baseline 0 each winter. Instead, it is carrying over anomalous warmth from one year to the next, effectively raising the floor for seasonal temperatures. That elevated floor is now high enough to support extreme storms well outside their traditional windows. The oceanic conditions did not just permit Sinlaku to form. They systematically removed every natural break that should have stopped it from achieving Category 5 intensity. And when the brakes are removed, the only remaining question is how fast the engine can possibly go. This immense reservoir of heat was the fuel source. Yet, fuel alone does not fully account for the storm's behavior. Something else allowed this system to ignite, to surge from an organized tropical disturbance into a 173 mile per hour monster in an astonishingly brief period. That process, known as rapid intensification, is emerging as one of the most perilous trends in modern meteorology. Super Typhoon Sinlaku did not build its strength gradually. It leaped to its peak intensity. The formal definition of rapid intensification is an increase in maximum sustained winds of at least 35 miles per hour within a 2-4 hour window. Sinlaku blew past that benchmark with ease. The storm underwent a period of explosive deepening that carried it from a strong typhoon to a super typhoon in a time frame that left operational forecast models struggling to keep pace. By the time updated advisories could be issued to reflect its new strength, the storm had already surpassed the previous forecast's upper limits. This is not an entirely new phenomenon, as rapid intensification has been documented for many decades. What has changed, however, is the frequency and magnitude of these events, a shift that the research community has been highlighting with growing concern. Analyses of tropical cyclone data, reaching back to the 1980s, reveal that the proportion of storms undergoing rapid intensification has risen significantly. More storms are now making larger jumps in intensity over shorter periods. Critically, these explosive intensifications are also occurring closer to coastlines, drastically reducing the time between an updated forecast and the storm's actual impact. One must pause to consider what this means for the effectiveness of our warning systems and the safety of coastal communities. The entire framework of emergency preparedness, from evacuation orders and shelter-in-place directives to resource prepositioning and hospital surge planning, is built upon the foundation of forecasts issued hours or days in advance. So long as a storm intensifies on a gradual, predictable curve, forecasters can provide communities with the lead time needed to act. But when a cyclone explodes from a Category 2 to a Category 5 overnight, that crucial window of lead time collapses. Residents who went to bed believing they faced a manageable event can awaken to an inescapable catastrophe. The gap in readiness between those two scenarios is immense. For the Commonwealth of the Northern Mariana Islands, this pattern of rapid intensification dramatically worsens an already precarious situation. These are small, remote islands with profoundly limited options for escape. One cannot simply evacuate an island like Tinian in the same way one might a city on the Gulf Coast. There are no inland highways leading to higher ground in a neighboring state. The only choices are to shelter in place or to depart by air or sea well before the storm's arrival. Both of these options depend entirely on a lead time that rapid intensification devours. The convergence of Sinlaku's explosive strengthening with its direct approach to the Marianas serves as a textbook case of the forecasting gaps that researchers have long warned about. The storm's evolution outpaced the predictions. And for islands where the margin for error is already razor-thin, where infrastructure is fragile and resources are scarce, losing even a few hours of warning can mean the difference between an organized response and total chaos. This event is part of a larger, more disturbing pattern that defines the story of Sinlaku in 2026. The issue is not merely that the storm was immensely powerful, nor that it moved so slowly. The true anomaly is that it intensified faster than anticipated, during a season when it should not have existed at all, feeding on ocean heat that should not have been available, and bearing down on islands that were in no position to be ready. It seems every single variable aligned simultaneously in the most destructive possible direction. And speaking of alignment, there is one more atmospheric factor that made all of this possible, a variable that unlocked the door for Sinlaku to achieve its full, terrifying potential. This brings us to the wind shear window. Wind shear is the invisible gatekeeper of a tropical cyclone's intensity. A storm can have access to the warmest ocean waters on Earth, an atmosphere saturated with moisture, and a perfectly formed circulation. But if the wind shear is too high, none of it will matter. The storm will be torn apart from within before it can ever mature. Put simply, wind shear is the difference in wind speed or direction between the lower and upper layers of the atmosphere. When this differential is high, the top of the storm is pushed in one direction while the bottom is pushed in another. This action tilts and disrupts the cyclone's engine, the towering thunderstorm columns known as convective towers, displacing them from the center. The energy that should be focused around the eye is instead scattered, causing the storm to weaken or preventing it from strengthening in the first place. During Sinlaku's most critical period of intensification, the wind shear across its environment was measured at a mere 5 to 10 knots. To truly appreciate what this means, we must look at the established thresholds. Shear values exceeding 20 knots are generally considered hostile to the development of a tropical cyclone. In contrast, anything below 10 knots is seen as highly favorable. Sinlaku, therefore, was operating within an atmospheric setting that offered virtually zero resistance to its vertical growth. With shear this low, the storm's convective structure was able to stack with perfect alignment. The circulation at the ocean's surface was in sync with the circulation high in the atmosphere. At the top of the storm, outflow channels remained symmetrical and highly efficient, cleanly venting waste heat away from the core. This allowed the eye wall to contract and intensify without being disturbed by disruptive crosswinds at high altitudes. Everything lined up perfectly. It is here that the compounding nature of this event becomes almost eerie. None of the individual factors at play, a warm ocean, low shear, or high moisture content, are unprecedented on their own. In any given year, one can find examples of each of these conditions. However, finding all of them at this extreme magnitude, in this precise combination, in this specific location, during the month of April, is the piece of the puzzle that deeply concerns climatologists. The frequency of these full alignment events, where every favorable condition converges at once, appears to be on the rise. It is much like rolling dice. Any single favorable factor is like rolling 1-6, not especially remarkable. But Sinlaku did not just roll 1-6. It was as if it rolled a 6 on every single die at the table, in a month when most of those dice should not have even been in play. As we zoom out and examine global tropical cyclone records, these perfect alignment events are appearing more often in seasons that were once quiet and in basins that were once considered marginal. The climate system is not just producing more fuel, it is also creating more opportunities for that fuel to be used at maximum efficiency. And when one of those rare opportunities happens to coincide with a slow-moving track directly over a populated island chain still recovering from the last disaster, the result is what we are witnessing now. But there is one more mechanical factor, one that has not yet received enough attention. It is the same variable I flagged earlier, the one that transforms all the other elements from dangerous into devastating. This is the forward speed problem. We must return to the figure of 3 knots, because it is not just a detail in this story. It is the variable that multiplies every other threat posed by this event. A tropical cyclone's forward speed is governed by the larger-scale atmospheric currents that steer it, such as the mid-latitude westerlies, the subtropical ridge, or the monsoon trough. The positioning of vast, high and low-pressure systems across thousands of miles dictates the storm's path. While the cyclone itself generates enormous winds internally, it moves across the globe at whatever speed this external steering flow dictates. When these steering currents are strong and well-defined, storms travel at a brisk pace. But when the currents are weak, disrupted, or caught between competing influences, storms can slow down, sometimes to a crawl. Sinlaku's crawl to 3 knots strongly suggests it became trapped within a weakness in the atmosphere's steering pattern. It was likely caught in a gap, a meteorological no-man's land between the subtropical ridge to the north and the equatorial flow to the south, where neither system was assertive enough to nudge the storm in a clear direction. The consequence of this atmospheric stalemate is a tropical cyclone of extreme intensity left to drift, nearly stationary, directly over inhabited islands. And it is at this point that the comparison to Hurricane Harvey becomes unavoidable once again. When Harvey stalled over Houston, it was not the wind that ultimately broke the city. It was the relentless passage of time. Time is what allowed the rainfall to accumulate, and time is what multiplies a storm's destructive power. For the islands under Sinlaku, time itself had become the primary adversary. Time is the critical ingredient for disaster. It is the time required for rain to gather, for rivers to swell past their banks, and for reservoirs to breach their limit. It is what transforms a dry neighborhood into a landscape submerged in waist-deep water. Typhoon Sinlaku was demonstrating this very principle, though on a different scale and to a community with its own unique vulnerabilities. The islands of the CNMI lack the extensive bayou and reservoir systems of a city like Houston, but they also lack its drainage capacity, its network of hospitals, and its mutual aid agreements with surrounding regions. Instead, they possess steep terrain that encourages flash flooding, limited options for shelter, and a painful history of incomplete recoveries from storms that came before. The mathematics of this rainfall amplification are as simple as they are devastating. Had Sinlaku been moving at a typical 15 knots, any location on the island of Tinian might have endured the storm's most intense rain bands for 2 or 3 hours. But at a crawl of just 3 knots, that same location is subjected to 10 or even 15 hours of the same torrential downpour. The total accumulation does not merely increase. It completely overwhelms every available mechanism for absorption and drainage. This is how a manageable hazard escalates into a full-blown catastrophe. The storm surge follows a similar, grim logic. This surge is created by powerful winds pushing ocean water toward the coast. As long as that wind persists from the same direction, the water continues to pile up. A fast-moving storm alters its wind direction relative to the coastline within hours, allowing the piled-up water to recede as the storm's geometry changes. A slow-moving storm, however, maintains that relentless pressure for far longer. The surge does not retreat. It lingers, it infiltrates, and it saturates everything. Structures near sea level, designed to withstand a temporary inundation, now face the fundamentally different challenge of prolonged submersion. There is a growing collection of research that suggests this phenomenon is not an anomaly. The hypothesis proposes that the average forward speed of tropical cyclones has been decreasing in certain ocean basins over recent decades. This trend is linked to larger shifts in atmospheric circulation, particularly a weakening of the steering currents that guide these storms across the open water. If this hypothesis is correct, and the data gathered so far indicates it has considerable merit, then the behavior of Sinlaku was not a statistical fluke. Instead, it offers a preview of an emerging class of storm, one defined by a devastating combination of extreme intensity and extreme duration. This fusion of power and persistence is something our infrastructure, our warning protocols, and our frameworks for recovery were never designed to handle. This extended duration fundamentally transforms the nature of the threat itself. It turns a windstorm into a massive flood event. It morphs a temporary surge into a force that can permanently reshape a coastline. It stretches a difficult night into a multi-day scenario where survival becomes the only objective. For islands already burdened by a recovery deficit, patched together time and again, and pushed beyond their financial and structural limits, such a transformation becomes an existential one. But then, another element was added to this crisis, something that occurred just hours before the storm made landfall. It was an event that had nothing to do with the atmosphere, but everything to do with how the human mind processes overlapping disasters. Roughly 6 hours before the eyewall of Super Typhoon Sinlaku began its assault on the Mariana Islands, a magnitude 5.5 earthquake occurred near the Pagan region of the island chain. The quake's focal depth was measured at 219 kilometers, classifying it as a deep-focus seismic event. That depth is significant for two key reasons. First, deep earthquakes are not uncommon in this part of the world. The Mariana Islands are situated directly over one of the planet's most active subduction zones, where the Pacific Plate dives beneath the Philippine Sea Plate. For residents of the Marianas, seismic activity is a constant, ambient feature of life. A magnitude 5.5 tremor, originating over 200 kilometers below the surface, would not typically be considered major news. Second, and this point is critical, there is no known physical mechanism that allows a deep focus earthquake to cause or influence a tropical cyclone, or for the cyclone to influence the earthquake. The processes of the Earth's lithosphere and the planet's atmospheric weather systems operate on entirely different scales of energy and time, and through different physical mediums. The earthquake did not trigger the typhoon, and the typhoon did not trigger the earthquake. They were two unrelated natural events that, by chance, happened in the same region within a 12-hour window. The human brain, however, is not a seismograph or a weather model. It is a machine built for pattern detection. When it observes two rare and powerful events converging on the same place at the same time, it instinctively draws a connection, whether one physically exists or not. For the people of the CNMI, who were already bracing for the most powerful storm in years, feeling the ground shake just 6 hours before the eyewall's arrival was not an abstract geological occurrence. It was a form of psychological compounding. It fostered a terrifying sense that everything was going wrong at once, that the universe itself was stacking threats in a way that felt deliberate, even when it was pure coincidence. This is precisely where the earthquake connects to the larger narrative we are following. The feeling of escalating, overlapping disasters is not irrational. It is just not caused by the specific mechanism people might assume. While the earthquake was not linked to the typhoon, the broader pattern of natural hazards, piling on top of one another faster than a community can process or respond, is very real. This pattern is not supernatural or conspiratorial. It is the logical outcome when any system becomes more energized and more variable. you simply get more events. These events are distributed randomly across time, and random distributions naturally produce clusters. When those clusters happen to land on the same population, the impact is not merely additive, it becomes multiplicative. This very pattern, this real and measurable increase in overlapping extremes, was unfolding across the entire United States on this exact same day. While Sinlaku was grinding its way across the Mariana Islands, the continental United States was simultaneously weathering its own cascade of extreme events. The simultaneity is the crucial point. Any one of these events would have been significant on its own, but occurring together on the same day, they paint a stark picture of a system running dangerously hot. Across the mid-Atlantic region, temperatures were approaching or shattering all-time records for April. Weather stations from Washington, D.C. to Philadelphia reported readings that were 15 to 30 degrees Fahrenheit above the norm for the middle of the month. These are not the kind of temperature deviations that are simply filed away as a warm day. These are departures so extreme they belong to a different season altogether, a clear signal of a system operating far outside its normal bounds. In the middle of April, an unseasonable heat began to settle over parts of the country, feeling more like late June. The temperature records being broken were not recent or trivial. Some had remained unchallenged for decades. This anomalous warmth was more than just a curiosity. At the very same time, the Storm Prediction Center issued an enhanced risk for severe weather across Iowa and the Great Lakes region. This designation, the third level on a 5-tier scale, signaled forecasters' confidence in the development of significant thunderstorms, carrying the potential for tornadoes, destructive hail, and powerful wind gusts. It was a threat that loomed over millions of people across several states, a volatile atmospheric collision fueled in part by that same record-breaking surge of warm, moist air moving north to meet a disturbance in the jet stream. Meanwhile, a different kind of elemental threat was gathering across the high plains, where 13 separate red flag warnings were active. Such warnings are issued when conditions become perfect for the ignition and rapid spread of wildfires, characterized by low humidity, strong winds, and parched vegetation. To have 13 of these warnings simultaneously in a single region signifies a major fire weather event, one that strains resources and demands attention across multiple states. And as the plains faced the risk of fire, parts of Michigan and Wisconsin were already contending with water. Persistent rainfall had completely saturated the soil, causing rivers to swell and overflow their banks, leading to active flooding. It was as if every element was in a state of simultaneous, chaotic expression. Taking a step back to view the situation from the perspective of national emergency management reveals a truly staggering picture. On a single day, the United States was grappling with a super typhoon striking one of its inhabited territories, a record-setting heat wave across a major population corridor, a significant tornado risk in the Midwest, critical fire weather on the plains, and ongoing floods in the Great Lakes. The National Weather Service had issued a cascade of alerts, with the total number of active warnings, watches, and advisories reaching 303 simultaneously across the nation. This wasn't just a series of isolated incidents. It was a nationwide tapestry of crisis unfolding in real time. Each of these distinct events had its own immediate or proximate cause. The heat was the result of a specific atmospheric ridge pattern. The severe storms were driven by a particular frontal boundary and jet stream configuration. The fire weather was a product of seasonal dryness combined with high winds. In a simple causal chain, none of these phenomena are directly connected to one another. The critical question, then, is what unites them. They are all occurring within the same overarching climate system, and the fundamental baseline of that system has shifted. A warmer global average temperature translates into more energy held within the atmosphere. This excess energy allows for greater moisture transport, creates stronger temperature contrasts, and fuels more intense and prolonged heat events. It also provides the fuel for more vigorous and dynamic storms. The climate dice, as it were, are not loaded to favor any single type of disaster. Instead, they are loaded to favor more extreme events in general more frequently. When you roll those loaded dice enough times, you inevitably get days like this. Days where the national map lights up with alerts from coast to coast, forcing the entire emergency management system to triage its response on a national scale. The central thread of this story, when viewed from 30,000 feet, is not about a single storm or a solitary heatwave. It is about an entire system generating overlapping extremes at a rate that outpaces the ability of our response infrastructure to keep up. The Super Typhoon Sinlaku was the most dramatic and destructive single event of this particular day, but it was just one piece of a much larger mosaic. And that mosaic, that interconnected picture of risk, is growing more complex with each passing year. As if to add a final, surreal layer to this already overloaded 2-4-hour window, something else was happening far overhead. During this same approximate period, an asteroid made a close approach to our planet, passing within 0.68 lunar distances of Earth. That is a proximity of roughly 165,000 miles, or about 2/3 of the way to the Moon. The object was entirely harmless. Its trajectory was well understood and meticulously tracked by astronomers, who had confirmed with precision that it posed zero risk of impact. On any other day, its passage would have been a minor scientific note. But on a day when a super typhoon and an earthquake were affecting American territory, while the continental US was simultaneously burning, flooding, baking, and facing tornadoes under more than 300 emergency alerts, an asteroid passing inside the Moon's orbit felt like a punchline being delivered by the universe itself. The event wasn't dangerous, but it pushed past the human brain's threshold for processing simultaneous anomalies. This asteroid is not part of the climate story, but it is a crucial part of the perception story. And on a day defined by overlapping extremes, perception is what drives public response, media narratives, and ultimately, political will. That number, 303, represents the staggering quantity of active warnings, watches, and advisories issued across the United States on this one day. It was a full spectrum of atmospheric hazards, from flood warnings and tornado watches to fire weather alerts and heat advisories, all lit up at the same time. This figure is more than just a headline. It is the result of a national stress test. Our emergency systems, from FEMA and the National Weather Service down to state and county level first responders, are all built with inherent assumptions about capacity. They are designed to handle a certain number of simultaneous events by shifting resources and activating mutual aid agreements. But 303 active alerts means there are very few quiet regions left to draw support from. The system begins to break down when fire crews in Kansas cannot be spared to assist with flooding in Michigan because they are facing their own emergency. It falters when search and rescue assets must be weighed against both a Pacific typhoon and an imminent tornado threat in Des Moines. The infrastructure was never designed for a scenario where nearly everywhere is in crisis at once. This leads to a dangerous phenomenon known as alert saturation, the point at which the sheer volume of warnings overwhelms the public's ability to process them. When a phone buzzes with a tornado warning while a person is still reading the heat advisory from an hour before, the cognitive load becomes too great. In such a state, people may simply stop reading the alerts and stop taking action. When every signal is an alarm, the greatest risk is that all alarms begin to fade into noise. Even the most precise warning system can lose its power when the people it is meant to reach are simply overwhelmed. This reveals an invisible danger inherent in a day of widespread crisis. The issue is not merely that the storms themselves are perilous, it is that the sheer quantity of simultaneous threats erodes the capacity of institutions and individuals alike to respond effectively to any single one. The entire framework for disaster response is being strained in ways it was never intended to handle. That strain manifests in tangible ways, in delayed reactions, in missed opportunities for evacuation, and in entire communities being overlooked as resources and attention are stretched thin across too many fronts at once. All of this points toward a recurring and troubling pattern of compressed recovery windows. Our planet's climate system appears to be generating more frequent and intense events, leaving far less time to breathe in between. The storm known as Sinlaku, therefore, is not some isolated catastrophe. Instead, it can be seen as one point of failure in a vast, interconnected network of stress that spans the globe, from the western Pacific all the way to the eastern seaboard of the Americas. This raises a fundamental question. Was this particular day a statistical fluke, a once-in-a-generation convergence of bad luck, or was it a sign of something new and far more concerning? Historically, the month of April is a quiet period in the tropical cyclone records of the Western Pacific. On charts that track accumulated cyclone energy over decades, April barely makes a mark when compared to the peak season, which runs from August through November. In most years, the month concludes without a single named storm forming in the entire basin. At most, a weak tropical depression might emerge, only to dissipate before ever gathering the strength of a typhoon. This is the established norm. It is what is expected. A super typhoon, with winds of 173 miles per hour, is not normal. It is not expected. And yet, it is not entirely without precedent. Though the examples are so scarce, they hardly constitute a meaningful category. Typhoon Hester, in 1966, stands as one of the very few documented instances of a storm reaching super typhoon intensity in late March or early April. At its peak in early April of that year, Hester was the equivalent of a Category 5 hurricane. The event was so extraordinary that it was largely regarded as a meteorological curiosity, something fascinating for a textbook, but not especially relevant for operational planning. The prevailing assumption was that a storm like Hester represented the most extreme tale of a probability distribution, an event with a return period measured in many decades, if not centuries. 60 years later, the arrival of Sinlaku, another super typhoon of comparable power in April, directly challenges that long-held assumption. While two data points do not form a trend in the strictest statistical sense, they do begin to narrow the realm of possibility. If events of this magnitude truly had a return period of, for example, 100 years, then having two of them occur within a 60-year span is unlikely, but not impossible. If the return period were closer to 50 years, it becomes far less surprising. And if the underlying environmental conditions are changing, if the baseline ocean temperature is rising, if the warm pool of water extends earlier into the year, and if wind shear patterns become more favorable in the spring, then the effective return period may be shrinking over time. This would make April super typhoons not just a possibility, but an increasing probability. This phenomenon is what meteorologists refer to as season creep. The boundaries that once defined the hurricane and typhoon seasons were never absolute, as nature does not follow a calendar. They were, however, reasonably reliable statistical guides. Entire systems were built around them. Insurance actuaries constructed their models based on these timelines. Building codes made reference to them, and emergency management agencies structured their plans around them. When those boundaries begin to blur, with the season effectively starting earlier and ending later, everything that depends on them must be recalibrated. But recalibration requires both time and political will, two resources that are often in short supply. The warmer baseline ocean temperatures that fuel these storms are not just providing energy for individual events, they are the very mechanism driving the expansion of the season itself. If the ocean reaches the thermal threshold required for cyclone development a full month earlier than it did in the past, then the window of opportunity for extreme storms widens by that same amount. When you multiply that effect across decades, you begin to see a world where an April super typhoon is no longer an outlier. It becomes an early arrival in a season that, functionally, never truly ends. This leads to a deeply unsettling thought. If this is what the expanded season can produce in its margins, a 173 mile per hour monster over United States territory, what might the peak of the season now look like? For anyone searching for a straightforward explanation, there is a fact that should be deeply troubling. The El Niño Southern Oscillation, or ENSO, is the single most dominant mode of natural climate variability on our planet. It is the cycle that modulates tropical cyclone activity across every ocean basin and serves as the go-to framework for explaining any unusual storm season. At the time of Sinlaku's formation, however, ENSO was essentially neutral. The official index was approximately 0.16, a value so close to zero as to be insignificant. The Pacific was not in a state of El Niño, nor was it in La Niña. It was neutral. The ocean was, in a sense, in the middle of the road, doing nothing remarkable at all. And therein lies the most paradoxical element of this entire story. Under normal circumstances, a neutral ENSO year is expected to produce moderate tropical cyclone activity in the Western Pacific, not suppressed and not enhanced, but simply moderate. The atmospheric conditions that govern a cyclone's formation and intensification are neither boosted nor inhibited by global teleconnections. One would anticipate a roughly average number of storms, with roughly average intensities, occurring within the roughly normal seasonal window. This is what the textbooks teach, what the models predict, and what decades of operational forecasting have been built upon. The entire system rests on the assumption that the ENSO state tells you more than any other variable what kind of storm season to expect. What you would never expect, and what no ENSO-based seasonal forecast would ever predict, is a 173 mile per hour super typhoon making landfall on US territory in the month of April. This is not a moderate activity event, nor is it even a high-activity one. It is an extreme, record-challenging storm occurring in the complete absence of any identifiable, large-scale climate pattern that could explain it. It is as if one were watching someone throw a 9-8 mile per hour fastball, only to be told they are not a pitcher and have never trained to be one. They are not supposed to be able to do this. And yet, there it is. A meteorological impossibility unfolding on the radar loop. Now, had Sinlaku formed during a strong El Niño year, we would have a tidy explanation. El Niño is known to shift tropical convection eastward across the Pacific, expand the warm water pool, and reduce wind shear in the Western Pacific's development region. In short, it creates the perfect conditions for tropical cyclones to form and intensify. The fact that this storm emerged without that powerful driver leaves us with a profound mystery. The usual suspect is missing, forcing us to look for answers elsewhere. Ordinarily, a powerful storm of this nature would have a clear and predictable cause, one that our seasonal forecasts would have anticipated. We would look to the El Niño Southern Oscillation, or ENSO, and see the familiar signature of an elevated risk. The event's timing might have been unusual, but its sheer intensity would have a plausible driver that scientists could agree upon, and the explanation would fit neatly within our established framework. But this time, that framework offers no simple answer. The ENSO state is neutral. The primary lever we expect to see pulled during major climatic events remains untouched. This absence of a familiar cause is, in itself, a profound clue, suggesting we must look beyond the cycles we know so well. It implies that another process is at work, one that does not cycle back and forth. ENSO is like a wave that travels across the ocean's surface, modulating conditions up and down. But what if the very surface itself is tilting? If the baseline temperature of the ocean is steadily rising, if the atmosphere holds more moisture, and if the conditions for cyclone formation are present across wider regions for longer periods, then even a neutral ENSO year can give rise to events that would have once been considered truly extreme. An analogy can help clarify this critical shift. For decades, we have watched ENSO as if it were a thermostat in a house, regulating the climate system. An El Niño phase would turn the temperature up, while a La Niña phase would bring it down, with the neutral state sitting in the middle. When an unusually powerful storm season occurred, our first question was always about the thermostat. But all this time, an unseen influence has been steadily raising the fundamental set point of the entire system. It is not the thermostat that has changed, but the baseline temperature around which it oscillates. As a result, when ENSO now cycles into its neutral position, what should feel like a moderate condition, the house is already hotter than it was during the most intense El Niño peaks of past decades. The oscillation is performing just as it always has, but the very floor beneath it has risen. And when that floor rises high enough, the system no longer needs the extra push from El Niño to generate extreme outcomes. In this new reality, a neutral state is now sufficient to power the extraordinary. The middle of the road has effectively become the old shoulder, the former edge of what was considered possible. This is the profound lesson that a storm like Sinlaku appears to be teaching us. The message is not that ENSO is broken. The cycle is operating exactly as it should. The fundamental problem is that the larger system it inhabits has shifted into a new state, one where a normal April day can provide enough energy to fuel a Category 5 Super Typhoon. The thermostat is cycling correctly. The house itself is simply and undeniably hotter. For years, researchers have been carefully tracking this underlying signal of a warming world. Of course, there is always a necessary and appropriate scientific caution when it comes to attributing any single weather event to long-term climate trends. Individual events are, by their nature, noisy, and distinguishing a clear signal requires statistical analysis over time. Yet, the emerging pattern within the global data is becoming increasingly difficult to explain by random chance alone. We are seeing a growing number of extreme tropical cyclones forming outside of the conditions that have historically accounted for them. These powerful storms are appearing more often in neutral ENSO years, during off-peak months, and in regions of the ocean not previously known for such activity. It is crucial to understand that our traditional frameworks have not become entirely useless. They still function as relative modulators of climate activity. An El Niño year, for example, will still tend to produce more cyclones in the Pacific than a La Niña year, which in turn tends to amplify activity in the Atlantic. In this sense, the dials of the climate system still turn in their expected directions. The profound change is that the absolute thresholds for extreme weather are now being surpassed, regardless of where those dials are pointed. This leads to bewildering paradoxes. A record-shattering Atlantic hurricane season occurs during a La Niña year, which is supposed to suppress Atlantic activity. A super typhoon forms in April during a neutral ENSO phase. The relative patterns we have long understood still hold. But the absolute outcomes are drifting far outside their historic envelope of possibility. As I reflect on events like this, a persistent thought returns. If the baseline climate continues to warm, and every major ocean heat dataset confirms that it is, then we are moving into an era where our traditional predictive models become progressively less reliable. This is not because their internal logic about ENSO's relative effects is wrong, but because they were calibrated for absolute environmental thresholds that no longer reflect our current reality. A forecast model stating that a neutral ENSO state equates to moderate cyclone activity is, in a technical sense, correct about the relationship. But if that moderate category now includes the possibility of an April super typhoon, the word itself has been stripped of its practical meaning. The model is not deceiving us. It is simply speaking a language that was defined for a cooler world. The storm known as Sinlaku, materializing in April under neutral conditions, feeding on ocean heat that should not have been available so early in the year, and intensifying with a speed that defied our models. This is yet another data point in a rapidly growing collection of events that our old frameworks cannot easily explain. This is not merely an academic curiosity. The implications should resonate with everyone, far beyond the fields of meteorology and climate science. It is a critical issue for emergency managers, for insurance actuaries calculating risk, for engineers designing our infrastructure, and most importantly, for the communities that lie directly in harm's way. The reason this matters so profoundly is that our entire infrastructure of safety, our forecasting systems, our emergency preparedness protocols, our building codes, and our financial risk models is calibrated to those older frameworks. They are all built on the assumption that the set point is stable. But when reality begins to consistently outpace what our models predict, those models must be updated. Until they are, communities remain exposed to dangers they are not being adequately warned about. People and governments make critical decisions based on what the forecasts tell them. If a model indicates that April is a low-risk month, communities may not prepare for a Category 5 storm. This growing gap between modeled forecasts and observed reality is not an academic problem. It is a question of survival, measured in evacuation orders that arrive too late and in shelters that were never opened. Ultimately, the most pressing question is not about the specific mechanics that created this single storm. The physics are well understood: a warm ocean, low wind shear, and abundant moisture. The deeper, more urgent question is this: how often will these perfect conditions now align? How frequently will the new, elevated baseline of our climate system be sufficient, all on its own, to produce events that once required the powerful, additional push of an El Niño? How many more April super typhoons will be born from a climate that we once called neutral? When outcomes consistently exceed our models for disaster, a difficult question arises: how long can we wait before recalibrating our frameworks and our entire posture of preparedness? To find an answer, we need only look at a simple timeline. Part 15, the rebuild gap. Consider three names spread across just 8 years: Yutu in 2018, Mawa in 2023, and Sinlaku in 2026. If you mark these dates without any other data, a pattern emerges that is less about meteorology and more about stark mathematics. The average time between major cyclones striking the Commonwealth of the Northern Mariana Islands has shrunk from decades to mere years. This is not a gradual shift over some ambiguous period. Within a single generation, the gap between catastrophic storms has transformed from a rare, once-in-a-lifetime event to a recurring threat every few years. And on the other side of this equation is a devastating reality. The time required for recovery has not compressed. In fact, it has often grown longer, as each successive storm erodes the fiscal, structural, and institutional capacity needed to manage the rebuilding process. With storms arriving faster and rebuilding taking longer, these two trend lines are moving in opposite directions. At some point, they are destined to cross, and when they do, the very concept of recovery may become meaningless, because a community can never finish rebuilding before the next disaster arrives. Let us explore what this looks like in practice, as the abstraction can obscure the profound human reality. Following Super Typhoon Yutu in 2018, a storm that hit Tinian and Saipan with sustained winds of 180 miles per hour, the most powerful tropical cyclone ever to make landfall on United States soil. The CNMI was confronted with a reconstruction effort that would be measured in years and hundreds of millions of dollars. Federal disaster declarations were made, and FEMA deployed personnel and resources across the Pacific. Congress was asked for supplemental appropriations to address costs far beyond the territory's budget. The machinery of federal disaster response was activated, and it did deliver substantial assistance. Yet, the recovery was inherently slow. This wasn't due to negligence, but to the fundamental challenges of rebuilding a remote island territory. The availability of contractors was scarce. One cannot simply drive a construction crew to Tinian as one might to a hurricane-damaged town in Florida. Materials had to be shipped over thousands of miles of ocean, turning already strained global supply chains into critical bottlenecks. Skilled labor needed to be brought in and housed on islands where the housing stock itself had just been decimated. Every single step in the process took more time and cost more money than it would on the mainland. 3 years after U2, a significant amount of reconstruction work was still underway. While the power system had been partially restored, the full hardening of the infrastructure, the kind of investment that would make the grid resilient to another major storm, remained incomplete. The housing stock was still below its pre-storm quality, with many residents living in structures that were merely patched and repaired, not rebuilt to modern standards of typhoon resistance. Public infrastructure, including schools, medical facilities, and government buildings, was described as functional. But that word, functional, was carrying a heavy burden in the assessment. It meant the lights were on and the doors could open, but it offered no guarantee that these buildings could withstand another direct impact from a Category 5 storm. It was a fragile piece, a recovery that looked complete from a distance, but was deeply vulnerable up close. Then, in 2023, Mawar arrived. It brought another storm, and with it, another wave of damage to systems that had not yet finished recovering from the last one. It is important to contemplate what this means for the people who live through this cycle. Imagine spending 3, 4, or 5 years watching your community slowly piece itself back together. Your roof is finally fixed, the local school reopens, and the power stays on for weeks at a time. A sense of normalcy begins to return, and then the satellite imagery lights up, and a forecast track draws a line directly over your home. You realize you are about to endure the entire ordeal once more. This time, however, the starting point is worse. The buildings are weaker, the budget is smaller, and the collective will is more fragile. The timeline for recovery resets, but it does so from a lower baseline. Each new beginning starts from a deficit that the previous recovery never managed to close. It is like attempting to fill a basin while the plug is pulled at increasingly shorter intervals. You never quite reach the level you had before, and with each draining, a little more of the foundation is eroded away. Now, consider Sinlaku in 2026, 8 years after U2 and just 3 years after Mawar. The islands are once again absorbing a catastrophic cyclone. The infrastructure it strikes reflects not just the damage from the current storm, but the accumulated, compounded, and layered damage from every storm that came before it, and from every recovery that fell short of completion. The concrete that is now cracking under Sinlaku's 173 mile per hour gusts was not poured fresh. It was patched after U2, patched again after Mawar, and is now facing a new onslaught with the structural integrity of a wall that has been broken and glued back together twice. This reveals a sobering truth about how resilience is not infinite. It is a resource that can be depleted over time. This relentless cycle forces disaster researchers and policy planners to confront a question that has no comfortable answer. Is this sustainable? The question is not whether the islands can survive any single storm. They have, repeatedly, and with extraordinary resilience, and at an enormous human cost. The people of the CNMI are not fragile. They have endured circumstances that would break most communities. The true question is whether the accelerating frequency of these events allows for any meaningful recovery at all. It is a question of whether recovery itself is an achievable goal when the next disaster arrives before the damage from the last one has been repaired. There is a point at which this recovery gap becomes structural. It ceases to be a temporary funding shortfall that a supplemental appropriation can fix, or a logistical delay that better planning can shorten. Instead, it becomes a permanent condition where the community exists in a state of perpetual, partial recovery. In this state, infrastructure is always somewhat degraded. Housing quality is consistently below the codes required for new construction. The power grid is always just one bad storm away from collapse, because the upgrades that could have prevented it were never finished before the last bad storm hit. The economic base is forever operating under the weight of storm debt. This is the quiet crisis unfolding not in a single, dramatic event, but in the slow, grinding erosion of a community's ability to ever be whole again. When a community is repeatedly struck by disaster, resources meant for development, education, and healthcare are perpetually diverted to the task of repair. The social fabric itself begins to fray under the strain of displacement and the profound psychological weight of knowing the next catastrophe is not a question of if, but when. And with each passing cycle, when seems to draw ever closer, it is important to recognize that this is not some distant, abstract scenario. This is the lived reality for an American community, for United States citizens. They hold American passports and contribute to the same federal systems, theoretically entitled to the same protections as anyone in Houston, Miami, or San Juan. Instead, they are ensnared in a devastating pattern of destruction and partial recovery, one that is accelerating beyond their capacity and perhaps anyone's capacity to manage with the frameworks currently in place. The predicament of the Northern Mariana Islands is a stark warning, but it is not unique. Throughout the Pacific, small island nations are confronting the same unforgiving arithmetic on their own shores. Across the Caribbean, communities ravaged by Hurricanes Maria and Irma in 2017 are still in the process of rebuilding, bearing the scars and watching each new storm season with the dreadful awareness that their infrastructure cannot withstand another direct impact. This pattern is emerging on coastlines all over the world. The frequency of major storms is now outpacing our ability to recover. While the interval between disasters shrinks, the time required to rebuild remains unchanged. The widening gap between these two timelines is a space where communities are slowly ground down, their resilience eroded with each successive event. As a U.S. territory, however, the CNMI holds a distinct and deeply uncomfortable place in this narrative. The federal government has a clear, constitutional, and moral duty to ensure the safety and recovery of its citizens in the Northern Marianas. On paper, the institutional power to act is immense. FEMA has a direct mandate, Congress holds the authority to allocate funds, and the Department of Defense maintains significant assets in the region. And yet, this formidable federal response infrastructure is increasingly tasked with addressing multiple, overlapping disasters at the same time. This is precisely the scenario that a day with 303 active weather warnings so vividly illustrates. When the entire nation grapples with extreme events, simultaneously with wildfires on the plains, floods near the Great Lakes, tornadoes in the Midwest, and a super typhoon in the Pacific, resources must be divided. Attention must be shared. And history shows that remote territories with small populations and no electoral votes tend to lose this competition for focus when the mainland is also suffering. This is not a cynical view. It is a conclusion drawn from the patterns of every previous disaster cycle. This rebuild gap is not some abstract risk looming in the future. It is a present and active reality. It is unfolding at this very moment on islands being battered by the most powerful storm on the planet. These are islands that were still mending the damage from the last major storm, which itself arrived before the repairs from the storm prior to that were even complete. It is a ratchet that turns in only one direction. With every click, the community's baseline of stability drops a little lower, its infrastructure degrades a little further, and the chasm between its current state and the resilience needed for the next event grows wider, and it is widening still. At this stage in our story, an obvious question naturally arises, one you may already be considering. Are catastrophic events truly becoming more frequent, or does it merely feel that way? It is a fair and vital question. The honest, if complex, answer is that both are true, and the fact that it is both is precisely what makes this situation so profoundly difficult to navigate. Our minds are not naturally suited to holding two seemingly contradictory truths at once and assigning each its proper significance. This ambiguity creates a challenge for our understanding. Human beings are fundamentally hardwired for pattern detection. It stands as one of our most significant cognitive advantages and is a primary reason we thrived as a species. This is the ability that allows us to infer a predator from a rustle in the tall grass, to predict an approaching storm from a change in the sky, or to connect two occurrences and derive a rule that enhances our survival. The search for patterns is the very foundation of science, of medicine, and of every system we have ever engineered to comprehend and manage our environment. It is, without any exaggeration, among the most powerful tools that evolution has ever crafted. Yet, this same powerful tool is also the source of one of our most dependable cognitive traps. When we observe 2 or 3 unusual events happening in close succession, we instinctively begin to construct a narrative that links them. An earthquake occurring just 6 hours before a typhoon must surely be related. A heat wave on the East Coast coinciding with a tornado outbreak in the Midwest cannot be a mere coincidence. An asteroid passing by at the same time a map displays over 300 active warnings feels like a sign that something larger is afoot. Our brains take these coincidences and weave them into a story of escalation, a feeling that events are spiraling, that unseen forces are converging, and that the entire system is breaking down in real time. This feeling is potent and visceral, and while it is not entirely incorrect, it is not entirely correct either. The space between that feeling and the objective reality is where a great deal of confusion and poor decision-making can take root. In the field of statistics, this human tendency is known as the clustering illusion. Gaining an understanding of it is crucial if we are to make sense of a day like today, allowing us to avoid both the panic that goes beyond the evidence and the dismissal of real signals, simply because they are entangled with random noise. It asks us to be both cautious and critical in our interpretations. Random events, when distributed over time, do not spread out evenly. They have a natural tendency to clump together. This idea is not intuitive, because when we imagine randomness, we often picture an even distribution of events spaced out at regular intervals, like fence posts lining a road. But true randomness is not so neat. It is inherently lumpy. The Poisson distribution, a mathematical model used to describe the timing of independent, random events, actually predicts that these clusters will occur purely as a result of chance. It's not that they might occur, they are statistically expected to occur. Some years will have more events than the average, and some will have fewer. This variation is itself an expected feature of the system, rather than a definitive signal that the system itself has fundamentally changed. Perhaps the simplest way to illustrate this is with a thought experiment. If you were to flip a fair coin 1,000 times, you would almost certainly observe long runs of 10, 12, or sometimes even 15 heads in a row. These streaks are not evidence of a biased coin or an external force at play. They are simply the natural, expected outcome of a random process. Chance, by its very nature, creates clusters that can look deceptively like meaningful patterns. If you flip a coin enough times, you will inevitably see long strings of consecutive heads. This doesn't happen because the coin is weighted or some unseen force is at play. It happens because this is the nature of true randomness. Our minds, however, are wired to see such a cluster and instinctively search for a cause. This phenomenon is known as the clustering illusion, where a real pattern is perceived, but the assumed cause is an invention of our intuition. Telling the difference requires looking past instinct and turning to data. So, when a single day brings news of a super typhoon hitting US territory, an earthquake shaking the same island chain, an asteroid passing within the moon's orbit, record heat in the mid-Atlantic, tornado warnings across the Midwest, and 13 red flag fire alerts on the plains, it's natural to feel that something is profoundly wrong. A part of this reaction is the clustering illusion at work. It's crucial to recognize that some of these events are mechanistically separate. The asteroid's path was determined billions of years ago by orbital mechanics, entirely disconnected from our climate. The earthquake was a tectonic process, the result of plate subduction unfolding over millions of years. To weave these disparate events into a single, escalating narrative is a cognitive shortcut, our brains finding patterns, even when the links are merely coincidental. This is often the point where the conversation can go astray. Hearing about a cognitive bias like the clustering illusion can lead some to a comforting but deeply flawed conclusion that the problem is imagined and everything is fundamentally fine. It's vital to be clear that this interpretation is not only incorrect, but dangerously so. The existence of the clustering illusion does not mean the underlying trends are unreal. Instead, it presents us with a critical task: to separate our perception of clustering from the statistical evidence for a trend. Each must be evaluated independently, on its own merits and with its own specific data. We are being asked to carefully distinguish the meaningful signal from the surrounding static. And when we perform that separation, setting aside the asteroid and the earthquake to focus squarely on extreme weather, the data tells an unambiguous story. Over the course of the satellite era, the global number of Category 4 and 5 tropical cyclones has demonstrably increased. This is not a minor fluctuation. The proportion of storms achieving these highest levels of intensity has shifted upward across multiple ocean basins, a finding confirmed by various analytical methods. Furthermore, a greater percentage of storms are now undergoing rapid intensification, the kind of explosive, forecast-defying strengthening that Typhoon Sinlaku exhibited. Underpinning this is a fundamental physical reality. Sea surface temperatures have risen in virtually every ocean on Earth, and the frequency of extreme precipitation has increased in many regions, consistent with the physics of a warmer atmosphere holding more moisture. In the United States, the number of billion-dollar weather disasters has roughly tripled per decade over the past 40 years, a stark trend that holds even after adjusting for inflation, population, and property values. This is a narrative written not by feelings, perceptions, or the anxieties of social media. It is a story told by measurements, taken by instruments, recorded in datasets, and analyzed by researchers. These conclusions have been published in peer-reviewed journals and replicated across independent groups using different methods. The consistency of this evidence is what gives it such weight. The signal is real. The reality we face, then, is a layered one, requiring us to hold two seemingly contradictory thoughts in our minds at once. This can be uncomfortable, but it is necessary. On one hand, yes, the feeling that everything is happening at once is partly a product of normal cognitive bias, amplified by how we consume information in the year 2026. Social media algorithms collapse every disaster into a single continuous feed. Around-the-clock news cycles give every extreme event maximum visibility, and our phones buzz with alerts from different states in a single afternoon. Our information environment, whether by design or by accident, is structured to make these clusters feel more intense than they might otherwise. A generation ago, the earthquake near Pagan and the red flag warnings in Kansas would likely not have appeared on the same screen at the same time. Today they do, and our brains instinctively process them as a single, escalating story. But beneath this layer of cognitive bias and social media amplification, there is a real, measurable, and physically grounded signal. The climate system itself is changing, producing more extreme events in more places throughout more months of the year. The intervals between these events are shrinking. This is the crucial distinction we must make. The coincidence of a typhoon and an earthquake on the same day is noise. However, a super typhoon forming in April during a neutral ENSO year and over abnormally warm ocean water is a powerful signal. The passing asteroid is an irrelevant distraction, but 303 simultaneous hazard warnings across a nation facing heat, fire, floods, and tornado risk all at once? That is the result of a stress test on a system being pushed beyond its original design. Separating these categories is not an academic exercise. If you lump everything together, you risk either panicking about things that are merely coincidental or dismissing everything because some of it is. Both reactions, paradoxically, lead to the same destination: inaction. The challenge ahead is one of mental discipline for all of us, from scientists and journalists to policymakers and citizens. It is the challenge of holding both truths at once, to acknowledge our cognitive biases without using them as an excuse to dismiss a proven trend, and to see the real patterns without inventing connections that are not there. We must feel the weight of a day filled with alerts, without surrendering to a sense of fatalism. The task is to respond to the evidence as it actually exists, not as we might wish it to be, nor as conspiracy theorists frame it, nor as the algorithm serves it up to us. We must listen to what the instruments record and what the laws of physics explain. On a day like today, that evidence is difficult to ignore. The ultimate question is not whether we are paying attention, but whether we are paying attention to the right things. For the new normal we are entering is not defined by any single event, but by the changing system that produces them. For those who have been following the stories we explore on Calm Space, a pattern may have become apparent. We often examine individual extreme occurrences, storms that shatter records, heat that feels truly unprecedented, cyclones forming in unexpected places, or spikes in solar activity that capture our attention. It is natural to view each of these as a self-contained story, an event to be analyzed and then filed away as we await the next major headline. This is the rhythm of the news cycle, and perhaps even the way our minds are wired to process information. When something dramatic occurs, we give it our intense focus for a short time, but then the window of attention closes, and we move on. But the story of Sinlaku compels a different kind of conversation, one that resists being neatly packaged. If you have journeyed with us this far, you can likely sense this as well. Sinlaku is not a standalone event. Every element we have examined is intricately connected to another, and that connection leads to yet another, weaving a tapestry that only grows more complex, more layered, and more systemic with each thread we pull. This complexity arises because what we are observing is not simply an event, but a single data point within a much larger pattern. This pattern is not about any one storm, heat wave, or disaster. Instead, it speaks to the behavior of an entire system. That system is Earth's climate, the vast, interconnected web of oceans, atmosphere, ice sheets, and land surfaces, all governed by the flow of energy that dictates what kind of weather is possible, where it can happen, and when. And the fundamental truth is that this global system is accumulating more energy. This is not a controversial claim, a political stance, or the output of a predictive model. It is a direct measurement, a physical reality recorded by our instruments. In the oceans, sensors have documented rising thermal energy content in nearly every basin. On land, atmospheric monitoring stations have registered an increase in baseline temperatures across every continent. And from orbit, satellite data confirms that there is more moisture in the atmosphere, a finding consistent with the Clausius-Clapeyron relation, a basic principle of physics stating that warmer air can hold more water vapor, at a rate of about 7% for every degree Celsius of warming. These are recorded, verified numbers, and they remain true regardless of personal opinion. The critical question, then, is how this additional energy reveals itself in our daily lives. It does not manifest as a single, obvious catastrophe that we can point to as the definitive signature of a changing climate. This common misconception is one of the greatest barriers to public understanding. Instead, what the extra energy does is shift the entire statistical distribution of weather events. We can visualize this with a bell curve, the familiar shape that illustrates the probability of various outcomes. On this curve, most days and most weather events cluster around the average, while extremes are, by definition, rare occurrences found at the far ends. This is how the system has always functioned, but when you add energy, the entire bell curve shifts. The center moves to a higher point, meaning what was once an unusually warm day becomes the new normal. Consequently, what was previously a normal day now feels unusually cool. And out on the tails of the curve, where the extremes reside, this shift has a disproportionate impact. Events that were once extraordinarily rare, like 1-in-100-year storms or 1-in-1,000-year heat waves, become significantly more probable. The system isn't doing something fundamentally new. It is simply operating from a higher energetic starting point, allowing the extremes to reach further, hit harder, and appear with greater frequency. Here we find the crucial insight that connects all the phenomena we have discussed. As extreme events of different kinds, from heat waves and severe weather to wildfires and intense cyclones, all become more frequent, the probability of them overlapping increases not in a simple, linear fashion, but exponentially. If the likelihood of each individual hazard goes up, the chance that 2, 3, or even 4 of them will occur on the same day rises dramatically. The mathematics is similar to rolling dice. If you roll a single die, getting a 6 is unremarkable. But if you roll 5 dice and all of them land on 6, you know something unusual has occurred. In the case of our climate, it is as if the dice are loaded not by much, but just enough that a full table of 6s starts appearing far more often than the old odds would ever predict. This recognition marks the transition from thinking about single events to thinking about entire systems. It is a profound shift in perspective, and one that is essential for understanding not just Sinlaku, but the trajectory we are on. This new perspective changes the very questions we ask. Instead of asking why a particular storm happened, a question that often has a specific and contained answer, we must ask why the background conditions have become so favorable for storms like it to occur more often, earlier in the season, and with less recovery time in between. This is a harder question, one that doesn't fit neatly into a headline, but it is the correct one. Rather than asking why heat records were broken in April, we should ask why the baseline temperature from which April's weather emerges is now high enough to produce such record-shattering anomalies during what ought to be a transitional season. Instead of wondering why 300 warnings were active on a single day, we must ask why the system is now capable of producing so many simultaneous extremes that such a number is even plausible. The answers to these deeper questions all point in the same direction: more energy in the system, higher baseline conditions, shifted statistical distributions, expanded seasons for hazards, and compressed intervals between them. The reality of these overlapping events was starkly illustrated on one single day. There was Typhoon Sinlaku, a storm of astonishing intensity reaching 173 miles per hour in April. That same day, an earthquake struck an unrelated geological event, but one that compounded the strain on the same community at the same time. Across the nation, 303 active weather warnings were in effect. The Mid-Atlantic experienced record heat that would have been notable in July, let alone April. Fire weather alerts were issued across the plains, with 13 red flag warnings active simultaneously. The Midwest faced a significant tornado risk, fueled by the same anomalous warmth that was feeding moisture into a collision zone with the jet stream. In the Great Lakes region, persistent rainfall on already saturated ground led to flooding, and as if to underscore the feeling of a world under pressure, an asteroid passed within the moon's orbit, a celestial event entirely separate from the rest, but one that added to the psychological weight of a day that already felt overwhelming. It is essential to reiterate that none of these events directly caused one another. I have stated this multiple times, and it bears repeating, because the distinction is critical. The earthquake did not trigger the typhoon. The heat wave did not summon the asteroid. These were independent occurrences. The connection between them is not one of direct, linear causation. Rather, the link is their shared context, a global system under increasing energetic stress, a system where the probability of independent disasters striking at the same time is on the rise. This is the true nature of the challenge we face, not a series of isolated incidents, but a systemic shift in the very character of our world. Though they manifest as distinct atmospheric events, a typhoon here, a heat wave there, or severe weather patterns that bring fire or flood, they all originate from a single, shared driver. Each is an expression of a global climate system now operating at a much higher energy state than the one that shaped our infrastructure, our predictive models, and even our fundamental intuitions. Their occurrence within the same 2-4-hour window is not the result of a conspiracy, divine will, or some singular, unified force. Instead, it is a matter of physics and statistics. A more energized system naturally generates more extreme events, and when more extremes are distributed across time, their overlaps become inevitable. This new reality brings with it a critical and sobering consequence. The windows for recovery are shrinking. We have seen this pattern unfold in devastating detail across the Commonwealth of the Northern Mariana Islands, which endured 3 catastrophic cyclones, Yutu, Mawa, and Sinlaku, in just 8 years. Each of these storms required a recovery period of nearly a decade for the islands to fully rebuild. This localized struggle, however, is merely one example of a growing global trend. Communities all over the world are discovering that the interval between disasters is now shorter than the time required to recover from the previous one. Whether in coastal cities, agricultural heartlands, island nations, or river valleys, the specific geography may change, but the underlying dynamic remains the same. The outcome is not a new, stable equilibrium that we can simply adapt to. It is a downward ratchet, where each cycle of destruction and recovery begins from a lower baseline, and each rebuilding effort reaches a lower ceiling. The trajectory has a clear direction, and that direction is down. In tandem with this decline, unpredictability is also on the rise. We now witness phenomena like super typhoons forming in April, a time when seasonal forecasts never anticipated them. Rapid intensification events outpace our operational models, collapsing the crucial window between a warning and the storm's impact. This forces us to question how we can prepare for a future that our own systems can no longer reliably predict. Heat records are no longer being broken by the fractional increments that statisticians would expect. Instead, they are being shattered by staggering margins of 5, 10, or even 15 degrees above normal, completely rewriting the statistical landscape. The old patterns that guided generations of planning, the seasonal calendars that signaled when to prepare and when to relax, the ENSO-based predictions that provided a framework for the year ahead, and the building codes designed around historical maximums are proving to be increasingly inadequate guides to our present reality. They are not necessarily wrong about the relative relationships they describe, but they are calibrated for a world that is rapidly receding in the rearview mirror. While this exploration may seem to focus on a single storm, Sinlaku, and the plight of the CNMI, the true story is far broader. It is about a trajectory, a curve on a graph that has been bending in the same direction for decades. That curve has now become so steep that individual data points a single storm, a particular heat wave, or a day with 300 separate warnings are reaching values that our old frameworks could never have imagined. And this is the crucial distinction. Unlike events, trajectories do not simply end. An event has a beginning and a conclusion. A storm arrives and eventually passes. A heat wave builds and then breaks. Floodwaters rise and then recede. They can be marked on a calendar and we can move on. Trajectories, however, operate differently. They persist, they compound, and they continue along their established course until a significant force, a decision, a fundamental change in the system alters their direction. As of now, nothing has altered this course. Until something does, every year will produce new data points, new records, and new communities, discovering that the world they prepared for is no longer the world they inhabit. Every single piece of infrastructure on the islands of Tinian and Saipan was engineered for a world that no longer exists. It is important to pause and consider that statement, because it may sound like hyperbole, the kind of dramatic overstatement a narrator might use for effect, but it is not. It is a stark engineering reality, grounded in the practical methods by which buildings, roads, power grids, and coastal defenses are designed, funded, and constructed. Understanding this is essential to grasping why the events unfolding on these islands represent more than just a natural disaster. They signify a systemic failure not of the people who built the infrastructure, but of the very assumptions they were given to build it around. In practice, infrastructure design follows a clear and established process. Building codes are fundamentally based on historical weather data. Engineers and code developers analyze records from a given period, typically the last 50 to 100 years, and extract the most extreme values observed. They identify the highest recorded wind speed, the maximum storm surge, and the most intense rate of rainfall. To these historical extremes, they add a safety margin, usually between 10 and 30%. Depending on the specific hazard and structure type, this calculation becomes the design standard, the definitive number that a building must be able to withstand. It defines the load a roof must resist, the height a seawall must reach, and the flow rate a drainage system must handle. A building code in the Mariana Islands, for example, naturally accounts for typhoon force winds, as typhoons are a known hazard in the Western Pacific. The code specifies wind load requirements, calculated from decades of historical typhoon data. It mandates roof tie-down specifications designed to resist the uplift forces seen in past storms. It sets concrete reinforcement schedules intended to prevent structural failure under the kinds of lateral loads that historical typhoons have generated. Furthermore, it establishes minimum elevation levels for construction in storm surge zones, based on the highest surge levels documented in the historical record. Every number written into that code can be traced back to a dataset, and every one of those datasets is bound by time, capturing what the climate did during a past period of observation. Herein lies the problem, one that extends far beyond the CNMI, beyond typhoons, and beyond any single type of hazard. The historical record is no longer a reliable guide to our current reality, and the gap between the two is widening with each passing year. When the strongest tropical cyclone ever to strike United States soil hit the islands in 2018, Super Typhoon Sinlaku, with its 180 mile per hour winds, the historical record was instantly revised. That single data point became the new extreme. In theory, the next round of code updates should incorporate this new information, and the design standard should ratchet up accordingly. But this reveals a system that is always looking backward, perpetually trying to catch up to a climate that has already moved on. For any new construction, it has become essential to acknowledge a new and documented reality. Category 5 landfalls on these islands are no longer a theoretical threat. This lesson was driven home when another major storm, Moa, struck in 2023, forcing yet another revision of the record. With two major events occurring in such quick succession, the dataset itself was transformed, altering not only the peak values, but also the fundamental assumptions about frequency. A building code designed around the premise that a Category 5 landfall was a once-in-50-year event now had to confront data suggesting the return interval could be dramatically shorter. The historical record was not just being revised, it was being rewritten in real time. This process accelerated when a third catastrophic cyclone, Sinlaku, hit just 3 years later in 2026. With winds of 173 miles per hour and a forward speed of only 3 knots, the storm lingered over the islands for the better part of a day. In that moment, the assumptions that underpinned every building, seawall, power line, and drainage culvert were invalidated. Tragically, the very structures built on those assumptions were being destroyed by the conditions that proved them obsolete. The critical insight here is that the infrastructure was not failing because it was poorly built. On the contrary, it was failing because it had been built correctly, but for a climate that no longer matched the one delivering the loads. The buildings had met the code, and the code was based on data, but that data had become obsolete. The time lag between the moment the climate shifted and the moment when codes, funding, and construction practices could catch up created a window of extreme vulnerability, a period in which communities are inevitably hurt. It is crucial to emphasize that the experience of the CNMI is not a special case, but rather an extreme one. The underlying dynamic of a mismatch between design and reality is playing out everywhere, across every type of infrastructure, in every region that faces weather-related hazards, which is to say, nearly everywhere on Earth. Consider the power grids across the United States, which were designed for historical temperature ranges. The transformers that step voltage down for residential use are rated for specific ambient temperature conditions. As summer heat waves exceed those conditions with increasing frequency and in more locations each year, the transformers begin to overheat. Their cooling systems are unable to keep up, causing efficiency to drop and failure rates to rise. This creates a dangerous feedback loop. At the very same time, power demand spikes as everyone turns on their air conditioning, pushing the electrical load above the generation and transmission capacity that was planned around historical peak demand. The result is often cascading blackouts, not because the grid is inherently broken, but because it was engineered for a temperature regime that has shifted out from under it. Coastal flood defenses tell the same story, just from a different angle. Seawalls, levees, tidal barriers, and beach nourishment projects were all engineered based on historical data for storm surge heights and sea levels. This data was carefully extracted from decades of tide gauge records and storm observations, and the designs even included safety margins. It was good, solid engineering. The problem arises when modern storms produce surges that exceed this entire historical envelope. This can happen because the storms themselves are more intense, or because they are moving more slowly, or because they arrive on top of a baseline sea level that has already risen several inches since the structure was first designed. When that happens, the defenses are overtopped. Water flows into places it was never meant to go, and the communities behind the wall, who believed they were protected, discover that their safety was calibrated to a past that is no longer predictive of the future. Drainage systems may offer the most universal example of this phenomenon. Every city, town, and developed area on the planet relies on some form of stormwater management, from storm drains and culverts to retention ponds and channels. These systems are all sized for specific rainfall intensities. A drainage engineer will calculate the expected flow from a storm of a given severity, for instance, a 1 in 2 5-year rainfall event, and then design pipes and channels large enough to handle that volume of water. The challenge today is that what was once a 1 in 2 5-year event under the old climate baseline might now be a 1 in 1 0-year event under current conditions. And the dreaded 1 in 1 0-0-year event, the kind of absolute worst-case scenario that only the most critical infrastructure is built to handle, might now occur every 30 or 40 years. The pipes themselves have not shrunk. The volume of rain has simply increased. So when a storm like Sinlaku sits over Tinian and Saipan, dumping 1 to 2 inches of rain per hour for 10 straight hours, the total rainfall exceeds the design capacity of every drainage system on those islands by a factor of 2 or 3. The system does not malfunction. It does exactly what the math says it will do when the inputs exceed the parameters. It overflows. Water runs across the surface, through buildings, down slopes, and into communities, carrying debris, mud, and everything else not anchored down. This is not a failure of mechanics, it is a failure of mathematics, because the math itself has changed. The infrastructure challenges in the CNMI are an extreme manifestation of this universal mismatch, but they illustrate the core problem with painful clarity. The gap between what we have built and what we now need is growing wider every year as the climate continues to shift. The infrastructure designed for the old regime falls further and further behind. Closing that gap requires more than just rebuilding damaged structures, which is what typically happens after a disaster. It demands rebuilding them to standards that account for the new reality. Higher wind ratings, greater surge resilience, increased drainage capacity, and the ability to withstand longer duration loads. Perhaps most importantly, it means designing for shorter return intervals between extreme events. This requires infrastructure to be more durable, more maintainable, and more resilient to repeated stress, rather than just a single peak event. Unsurprisingly, all of this is more expensive, significantly so. A building designed to withstand 180 mile per hour winds costs more than one designed for 140. A seawall built for 15 feet of surge costs more than one built for 10. A drainage system sized for the rainfall rates of an extreme tropical cyclone costs far more than one sized for typical thunderstorm runoff. These additional costs multiply across every structure, every system, and every piece of infrastructure on every island. The price tag for rebuilding the CNMI to genuinely storm-resilient standards, not just patching what broke, but creating something that can withstand the next Sinlaku, is staggering for a territory with a small economy and limited fiscal capacity. Beyond the immense cost, there is the challenge of time. You cannot simply throw money at reconstruction and expect it to happen overnight, especially on remote islands with constrained supply chains and a limited construction labor force. A comprehensive infrastructure rebuild of the CNMI, done to modern, resilient standards, would take years, even under the most ideal conditions. This leaves a difficult and prolonged period of vulnerability, a stark reminder of the race against time that many communities now face. In the wake of a disaster, the conditions for recovery are never ideal. This is a fundamental truth, and it demands a significant political commitment to fund infrastructure for a future that, by its very nature, has not yet arrived. Such funding must be secured based on projections that some stakeholders may still contest, all while competing against every other pressing demand on a nation's budget. This is the political reality. Asking lawmakers to allocate billions of dollars to fortify a territory that many citizens cannot even locate on a map presents a formidable challenge. This challenge is magnified when the goal is to protect against storms that current building codes do not technically require planning for, based on climate models that a portion of the political landscape actively disputes. It is an incredibly difficult task, one that must be undertaken again and again after every storm in a relentless, seemingly endless cycle. Even if we were to imagine a fantasy scenario with unlimited funding and absolute political will, a temporal problem remains that no amount of money can resolve. It is simply not possible to rebuild an entire island's infrastructure from the ground up when catastrophic storms are arriving every 3 to 5 years. The timeline required for construction far exceeds the interval between these destructive events. One cannot pour and cure concrete, fabricate and install steel reinforcements, lay subterranean utilities, reconstruct the power grid, rebuild the housing stock, and harden public facilities in just 3 years. This is an impossible feat on a remote island, and it would be nearly as difficult even on a mainland with complete logistical support. The clock simply runs out before the work can be finished. The result is a perpetual state of triage. Instead of a full rebuild, authorities must identify the most critical structures: the hospital, the emergency operations center, the main shelter facilities, and focus on hardening those first. They work to reinforce the communications infrastructure to ensure a link to the outside world is not severed. They patch the power grid just enough to restore basic services. Everything else, from schools and homes to commercial buildings and secondary road systems, is left to face the odds. The strategy becomes one of hope that the next storm will be weaker, that it will track farther away, that the island will simply get lucky. But when that luck runs out, when the next storm arrives at full intensity, the infrastructure is not ready. It could never have been ready in the time available. The damage compounds, the baseline for recovery drops even lower, and the devastating cycle begins anew. This is the precise situation that the Commonwealth of the Northern Mariana Islands finds itself in tonight. As the most powerful storm on the planet grinds overhead at a walking pace, the buildings absorbing its fury are not the ones that should be there. They are the buildings that time, money, logistics, and the cruel arithmetic of storm recurrence allowed to be there. The chasm between what they are and what they would need to be to survive this night intact was always destined to be filled by damage, by loss, and by the slow, exhausting realization that the world these islands were built for is not the world they now inhabit. Part 19. The Information War Layer. Within hours of Sinlaku's rapid intensification, and even before its eye wall made contact with Tinian, a familiar set of alternative narratives began to spread across social media. To call this pattern predictable is not to be dismissive. Rather, it is to acknowledge that this has become as reliable a feature of extreme weather as the storm surge itself. This sequence of events unfolds each time a major storm forms, strengthens quickly, and threatens a populated area. Before the first gust of wind strikes the first building, the conspiracy ecosystem awakens, launching a storm of its own in the digital realm. Some users immediately claimed the storm was evidence of geoengineering, a form of weather manipulation technology, supposedly deployed by unnamed government actors for unstated purposes. The specific allegations varied. A number of posts pointed to HAARP, the High-Frequency Active Auroral Research Program in Alaska. This facility has been a favorite target of weather-related conspiracy theories for decades. Despite being an ionospheric research station with absolutely no capability to influence tropical cyclones, others made vague references to cloud seeding operations. These theories conflated real but extremely limited technology, which can modestly increase precipitation under specific local conditions, with the fantastical ability to create or steer a Category 5 Super Typhoon across thousands of miles of open ocean. The leap in capability between these two things is roughly equivalent to the difference between lighting a match and detonating a nuclear weapon, a crucial distinction that is often lost in the endless scroll of a social media feed. Other narratives pointed to the proximity of United States military installations on Guam, such as Andersen Air Force Base and Naval Base Guam, as well as the broader strategic military presence in the Marianas. These posts speculated that the storm was somehow connected to classified weapons testing. The logic, as it was presented, followed a simple but flawed line of reasoning. The military is there, and the storm is there. Therefore, the military must have caused the storm. Some accounts went even further, suggesting the use of directed energy weapons or advanced atmospheric manipulation technology being tested under the cover of a natural disaster. A subset of these theories even attempted to link the typhoon to a magnitude 5.5 earthquake that occurred 6 hours before landfall, claiming the seismic event was evidence of tectonic weapons or underground detonations designed to destabilize the region in concert with the atmospheric assault. It is important to address these claims with straightforward clarity. None of them are supported by any evidence. There is no partial support, no ambiguous support. There is simply no support at all. The technology required to accomplish what is being claimed does not exist. The ability to create a tropical cyclone from scratch, to organize convection across hundreds of miles of ocean, to spin up a vortex with sustained winds exceeding 170 miles per hour, and to maintain that system for days as it tracks across the Pacific, is not a classified secret. It is not hidden away in some government facility. It is a scientific and engineering impossibility with our current understanding of physics. The energy budget of a mature super typhoon is so astronomically large that no human technology comes within orders of magnitude of replicating it. We cannot create these storms. We cannot steer them. We can barely predict their paths with accuracy more than a few days in advance. The notion that any government possesses the power to engineer what Sinlaku became is not a fringe theory deserving of respectful debate. It is a fundamental misunderstanding of the scale of energy involved. The physics governing the formation and intensification of tropical cyclones are, in fact, well understood. We have explored them in detail. The necessary ingredients, the immense ocean heat content, the low wind shear, the abundant atmospheric moisture, the collapse of steering currents, and the dynamics of rapid intensification were all present. Every single aspect of Sinlaku's behavior is consistent with the observed environmental conditions. There is no residual mystery that requires an exotic explanation. The truth, in this case, is not hidden in a conspiracy, but is plainly visible in the environmental data. The ocean was anomalously warm, and nature simply took its course. The atmospheric conditions were, in fact, unusually ideal for a storm of this magnitude. The cyclone's behavior aligned perfectly with the established principles of physics, developing exactly as a tropical system would under those circumstances. This provides a complete and scientifically sound explanation, though one that may not seem thrilling enough for a conspiracy narrative. The truth, in this case, is grounded in straightforward science. Simultaneously, a seismic event occurred. A deep focus earthquake, originating at a profound depth of 219 kilometers. This took place in one of the most seismically active subduction zones on our planet, the Mariana Trench System, a region that experiences thousands of earthquakes every year. A magnitude 5.5 tremor at that depth is certainly noteworthy, but it is not an extraordinary event for this area. Crucially, there is no known physical mechanism that could connect a tectonic event at such a depth to atmospheric conditions, or the other way around. The timing was purely a coincidence. Such coincidences happen, and they happen far more frequently than our pattern-seeking minds are comfortable admitting. This very inability to accept random chance is one of the core psychological drivers behind conspiracy thinking. Here, we must shift our focus from simple debunking to something far more consequential. The existence of these narratives is important, not because of any truth they hold, but because of their impact on the information environment. This is particularly dangerous during moments when clear, accurate information is most vital. It's a part of the story that often goes overlooked, less dramatic than the storm itself, but with the potential to be just as destructive. When a community is in the path of a super typhoon, when families must decide whether to evacuate their homes, when emergency managers are issuing directives that could mean life or death, the last thing anyone needs is for a large portion of the population to doubt the reality of the storm. They begin to question the trustworthiness of official warnings, or even believe the government itself secretly created the threat. These conspiracy narratives do more than just distract. They actively erode the trust upon which all emergency communication depends. This erosion of trust has devastating real-world consequences. If an individual believes the government is capable of engineering hurricanes, why would they ever trust that same government's evacuation order? If someone thinks the National Weather Service is complicit in a cover-up, why would they believe its wind speed forecasts? If they are convinced an earthquake was a weapons test, why would they follow guidance from the very military they suspect of causing the destruction? Each layer of conspiratorial thought strips away a layer of trust, and trust is the essential ingredient that makes emergency communication effective. You can have the most precise forecast in the world, delivered by the most skilled meteorologists on the planet, but it becomes meaningless if the people who need to act on that information do not believe it is real. In the face of a Category 5 landfall, confusion does not simply slow down a response, it can be lethal. A family might delay seeking shelter because they are unsure if the storm is a legitimate threat. A community leader might hesitate to open an emergency shelter after seeing social media comments claiming the storm is a hoax. A resident might choose to remain in a storm surge zone because they have been told online that the government is exaggerating the danger to advance a hidden agenda. These are not hypothetical situations. They are the documented outcomes of conspiracy-fueled distrust during natural disasters, and they are becoming more frequent as our information ecosystem grows more fractured and algorithmically optimized for engagement over accuracy. And here lies the part of this issue that is most deeply troubling for those who work in this field. The true explanation for what is happening is often far less dramatic than the conspiracy and much more difficult to summarize in a viral social media post. The reality is that our climate system is accumulating more energy. This, in turn, is shifting the statistical distribution of extreme weather events, increasing both the frequency and intensity of overlapping hazards. This compresses the time communities have to recover, which degrades infrastructure faster than it can be repaired or replaced. That is the real story, and it is a story that requires nuance. It demands an understanding of ocean heat dynamics, atmospheric physics, statistical distributions, infrastructure engineering, economic limitations, and policy timelines. It lacks a simple villain or a single smoking gun. There is no secret laboratory or shadowy government program. Instead, there are trends, probabilities, compound risks, and feedback loops that unfold over decades. Now, compare that complex reality to the simple phrase, "The government has a weather weapon." 6 words. They are instantly engaging, emotionally charged, and perfectly designed for sharing. They generate enormous interaction because people either passionately agree or vehemently disagree, and the algorithm rewards the engagement either way. The conspiracy post can attract 1 million views in an hour, while the careful scientific explanation gets buried. This is where evidence-based communication faces its most difficult trial, not in a laboratory, a peer-reviewed journal, or a scientific conference where everyone agrees on the basic methodology. The hardest test is in the chaotic information environment of an active disaster, where speed often triumphs over accuracy, and simple narratives outperform complex data. Here, the work of channels like Calm Space, of forecasters who studied fluid dynamics for years, and of researchers who dedicated their careers to building the knowledge that explains events like this must all compete in real time. They compete with content designed not to inform, but to exploit confusion. Content that doesn't need to be right, only first, loud, and emotionally resonant. The challenge, then, is not merely to debunk false claims. If that were all it took, the task would be simpler. One could just post the facts, cite the sources, and be done. The true challenge is to make the real story compelling enough that it doesn't lose the audience to simpler, more emotionally satisfying fictions. Because the true story that overlapping extreme events are increasing, that recovery windows are shrinking, and that communities are trapped in a worsening cycle demands action. Action requires understanding. Understanding requires attention. And a hinge is the very thing that is fractured and scattered when the information space is flooded with noise engineered to be more engaging than the truth. I don't have a simple solution for this. Nobody does. To truly counter misinformation, a simple correction is not enough. The only lasting defense is to build a genuine understanding of the world, grounded in evidence. Our journey through the physics, the data, and the mechanisms behind these events is meant to provide that foundation, allowing the logic to be evaluated on its own merits. You are not asked to believe because an authority tells you to, but because you can follow the chain of reasoning and see that it holds. This is how we build resilience against false claims, by making our understanding of reality so robust that they can find no purchase. The storm was real, the earthquake was real, and the pattern of escalating, overlapping hazards is also undeniably real. The explanation for this pattern lies not in conspiracy, but in physics. And this is where the true concern should lie, because the implications of the physical reality are far more serious than any geoengineering theory. A hypothetical weather weapon could, in theory, be switched off. The laws of physics, however, have no off switch. The immense heat absorbed by the ocean does not simply vanish when the news cycle moves on. The new, shifted baseline of our climate does not reset because a politician delivers a speech. The trajectory we have been tracing is one of more extremes, more frequent overlaps, and greater damage, with ever-shrinking windows for recovery. That trajectory continues, whether we are paying attention or not, and it will persist long after the conspiratorial posts have been forgotten and the algorithms have moved on to the next fleeting outrage. This is why the battle for clear information matters so deeply. It is not that the conspiracies are so potent in themselves. Most are too incoherent to inspire organized action. Their true danger lies in how they consume our collective attention and erode the trust we desperately need to confront the real problem. And that real problem is not going away. Let us return to the moment where this story began. As we speak, Super Typhoon Sinlaku is moving across the Mariana Islands, a stark illustration of these forces at work. At its peak, its intensity reached 173 miles per hour, yet its forward speed was a mere 3 knots. This agonizingly slow pace meant its eye wall lingered over communities for the better part of a day. It unleashed 15 to 25 inches of rain onto islands with steep terrain and limited drainage, while a storm surge of 10 to 15 feet battered coastlines where reefs and seawalls were already compromised. Seas swelled to 40 feet. All of this occurred on United States soil in April, a time of year when such a storm should be a historic anomaly. And just 6 hours before the eye wall made landfall, a magnitude 5.5 earthquake shook the very same island chain. While unrelated to the storm, it was a real and visceral shock to the same people who were sheltering from the most violent winds they had seen since Typhoon Yutu in 2018. A storm from which many people and much of their infrastructure had never fully recovered. While this crisis unfolded in the Pacific, the continental United States was simultaneously contending with 303 separate weather warnings of its own. The Mid-Atlantic was shattering April heat records, by astonishing margins of 15 to 30 degrees. Iowa and the Great Lakes faced an enhanced risk of severe weather, including potential tornadoes. Across the high plains, 13 red flag warnings for fire danger were active. At the same time, Michigan and Wisconsin were experiencing significant flooding. As if to underscore the sheer randomness of events, an asteroid also passed harmlessly within the Moon's orbit. It is crucial to understand that none of these events directly caused one another. The earthquake did not trigger the typhoon, the heat wave did not spawn the tornadoes. The asteroid, of course, had no connection to any of it. Yet they all took place within the same 2-4-hour window on the same planet, stressing the same national response systems. And the weather events all emerged from the same fundamental driver, a climate system carrying significantly more energy than the one around which we built our entire civilization. In this context, Sinlaku is not an anomaly, it is a data point. It is one more entry in a rapidly growing catalogue of events that exceed historical expectations. These storms arrive outside their traditional seasonal windows, compounding their destructive power by striking communities still recovering from the last disaster. They occur alongside other extremes, which collectively overwhelm the capacity of emergency systems that were designed for a far less volatile world. This reality is creating a widening recovery gap. The interval between Typhoon Yutu and Typhoon Mawar was 5 years. The time between Mawar and Sinlaku was just 3. With each successive blow, the infrastructure was less ready, the budgets were more depleted, and the buildings were not yet whole. It is a relentless downward ratchet, and the next storm, whenever it arrives, will find these islands once again only partially rebuilt, partially functional, and partially prepared. We are witnessing the very definition of a season becoming obsolete. Super typhoons in April were once considered once-in-a-generation events, but as the ocean continues to warm and the deep pools of warm water expand, the conditions that fuel explosive intensification are occurring earlier and earlier in the calendar year. This forces a difficult question. What happens when a century of climate knowledge no longer applies? Imagine our forecasts, our building codes, our insurance models, and our very sense of preparedness all exist inside a box. The walls of that box are now moving outward. Everything we rely on must move with them, or be left behind by a new and more dangerous reality. The intensifying overlaps of these disasters are not the work of some malevolent coordinating force. They are the logical outcome of a more energized system that simply produces more events. When more events are distributed across time, they will inevitably cluster together more often by pure chance. The days when everything goes wrong at once are not being engineered. They are being statistically generated by a climate that is rolling more dice, more frequently. And tragically, our information environment is fracturing at the exact moment it most needs to cohere. While researchers work to communicate these compounding risks, the public discourse splinters into denial, conspiracy, and fatalism, undermining the urgent work of those trying to build a meaningful response. Eventually, Sinlaku will pass. The winds will subside, the surge will recede, and the rains will stop. The Commonwealth of the Northern Mariana Islands will begin the agonizingly familiar process of assessing damage, clearing debris, and rebuilding yet again. The headlines will move on. The asteroid will vanish into its long orbit. The heat wave will break, the fires will be contained, and the flood waters will drain. But the system itself will keep warming. The ocean will continue to accumulate heat. The dice will keep rolling. And the next day, like this one, the next day when everything stacks against us, when every warning light flashes, when a community that never fully recovered takes another hit from a storm that shouldn't exist in a month, it shouldn't arrive, that day will come again. It will come sooner than the last one, upon infrastructure weaker than the last rebuild, with recovery resources stretched thinner than ever before. This was never a story about one storm. It is a story about a pattern, and that pattern is accelerating. Here is a story of a system in profound transition, catching communities within its current and leaving institutions struggling to adapt. With every year, a gap widens between the world we prepared for and the one unfolding around us. This prompts a vital question, shifting our focus from why this happened to a more urgent inquiry. How often will it happen again?